Hello everyone, welcome back to your physics class. Now last time when we wrapped up things, you were working on some different assignments from Unit 1, which was all to do with the basic uh, analysis or basic calculations and techniques that you would need or that are required of this physics class and that you will be applying in a lot more ways uh, within the coming sections and the chapters that we're going to study. Today, however, we were going to start with Unit 2, which is all to do with one-dimensional kinematics or movements and all of those. It's kinematics is all to do with motion. Right, to start with, the very first thing that comes to mind when we're dealing with a motion of an object is, well, how to quantify it, that motion. And one of the best ways to do it, or one of the basic things to start with, well, is to do by measuring the distance, right? And that distance is, if the slide will move on, I don't know why it's not moving forward, but anyways, it's to do with distance. Now, there are two parts or two words that are commonly used, which are distance and displacement. However, there is a key difference between these two. Uh, Distance is the numeric measurement of space between 2 points. However, displacement is more to do with the shortest numeric measurement of space between 2 points. Does this make sense to get the difference? There's another important aspect, and that's to do with, if it doesn't make sense, wait, we'll move on to the next slide. Once we move on to the next slide, you will see how there's a picture, there's an image or two, which will help you with it. But there's an important distinction between these two, and that's to do with that both distance and displacement are measurements of space between 2 points, but essentially distance has got a magnitude only, whereas displacement's got a magnitude, so it's got some numeric value to it, and a direction as well, right? So I don't know if you've done scalar or vectors. We will be getting into scalar versus vectors, and then next chapter and all those vector relations. But most importantly, a scalar quantity is one that does not have any direction. It has a magnitude, but it has no direction. So in this case, distance is, so distance right here is your scalar quantity, whereas displacement is going to be your vector quantity because it's got both a magnitude and a direction as well. So moving on, if you recall this picture, this image from one of my first videos that I published, that was to do with my daily commute to CJ, right? So what I'd mentioned that is I'm living around the University of Dayton. I opened up Google Maps, and what I got was that there are different possible routes that I can take. One is that I go through, I'm forgetting the name of this street here, but I can go through Brown Street, um, and I can go through, I can cross the bridge, and there's another way to get to CJ, and I can go through Route 35, and that's another way to. So there are multiple options that I have to get to CJ, depending on how much time I have and whatnot, right? So these are the distances to CJ, and they're measuring without any direction how much the distance, or well, the total space I'm traveling to get to CJ. Whereas on this slide, this is taken from Google Earth because that's the only way I know how to measure straight line distance. But this is again the same start point, end point. So University of Dayton, CJ around here. Um, it's not very clear. I could not figure out how to get to layered map, so just similar as Google Maps. Uh, but on Google Earth, what it does is you can essentially point and measure the distance, a straight line distance from one location to the other. So the shortest distance in case from University of Dayton to CJ is about 1.22 miles, right? So that's my displacement. See, it says distance here, but that's another thing. It's like I said before, they're commonly interchangeable or they're interchangeably used in most commonly, right? So just to wrap things up, distance is again the shortest measurement space, not the shortest, sorry, the measurement of space between 2 points here, and for in this example, it's the University of Dayton and CJ, whereas displacement is the shortest, right? Shortest measurement of space between 2 points with a direction, right? So it's 1.22 miles north and west, right? So northwest that way. Um, so that's those are the definitions. Now, how are we measuring this? We are measuring this by a frame of reference. What is a frame of reference? Well, it's a system to pinpoint a location of an object within space, right? Um, in this case, we can take a reference point. Um, we'll get more into it, but reference frames are very important when you're trying to do anything um, in the physical world. So, for example, just let's talk about this image again. Since this is measuring displacement, uh, what could be my reference point? I could be measuring from St. Anthony's Catholic Church right here. And what would happen? I can measure my distance from St. Anthony's, sorry, displacement from St. Anthony's Catholic Church to the University of Dayton. And I can measure my displacement from St. Anthony Catholic Church to CJ, right? And that would be my one reference point, and the displacement between University of Dayton and CJ would not change, right? So I'm looking at University of Dayton and CJ while I'm standing at St. Anthony's Church, and then let's just say my vision's that good, but I'm looking at these 2 points, and that displacement is not going to change. If I were to move my reference point from St. Anthony's Catholic Church to, let's say, Emerson Academy, what's going to happen? My displacements to University of Dayton would change, and so would my displacement to CJ, right? That would change. But the displacement between University of Dayton and CJ with respect to Emerson Academy will still be the same, right? So it's the shortest distance that you can get between these two. So that reference point can change, and usually with frames of reference, what happens is that reference point is the origin. That's where you start measuring everything from, right? And once we get into 2D motion and whatnot, we will get more into this. But this is essentially what the frame of reference is doing. It's essentially giving you a point where you can extend an axis out in the x direction, let's say in the y direction, and then you can go up and down as well. So you can point upwards and you can point downwards. That all depends. Then you can measure elevation and whatnot. So you have 3D frames of reference most commonly, then you can have 2D to simplify things. 1D is less commonly used, that's why we're not going into it, but just simply looking at this, if I was standing at University of Dayton looking at CJ in a straight line with that, if none of these buildings were in the way, that would give me a 1D frame of reference. But that's not commonly used, so we're not using this. Um, so moving on, just expanding onto this, let's start from the point of view of our solar system, right? So solar system, here you've got the sun, Mar- Mercury, Venus, Earth, Moon, Mars, and whatnot. All these planets are around here, and they're circulating or orbiting around the sun, right? So here, the center point where we're observing our this little solar system. Again, we're not talking about the entire universe or galaxy here, but essentially we're talking about our solar system. We're measuring this by looking, or we're standing at the sun and then we're observing the motion all the other planets from that sun. So our reference point is going to be the sun here, starting here. So right, so we can do y-axis, x-axis, and then that's going to be our reference frame in this 2D plane that we are in, right? So it's just two-dimensional. We're not looking at the elevation or the tilt or whatnot. That's very complicated. I hope that makes sense. If it doesn't, please let me know in the Google form that I will be attaching with this document. If we were to zoom out, I'll look at our Milky Way, it's the same thing. Now, this is an image from the Hubble telescope. Um, and what you see here is the center is of the Milky Way is somewhere around here in this light zone, right? And this image on the top came out recently, and this pinpoints to this. The astronomers were saying that this was a black hole, and that was the center of the universe. But if you start reading this article on the NASA website, this is that black hole around here. So they're saying that the center of the universe could be this entire span here. They're still trying to pinpoint where that is, but that is essentially that what they're confining it to. So it could be around this little point here, right? And this image is basically trying to get rid of all this light dust, light cloud, or dust cloud that what they say, which is reflecting light towards the telescope. Essentially, they've gotten rid of that, and that's allowed them to take this image. But that's for another day. So finally, we can narrow down these things to the Earth system. So you can have if you go back to the solar system, we've got the Earth Moon system, which is going to be its separate thing. So coming back to Earth, what we've got here is then, if you consider ISS, since it was in the news recently because of the SpaceX flight, or the Dragon, Crew Dragon that went into International Space Station and then came back. That uses its own reference frame. So, right, when we're talking about the elevation or from the Earth's center, when we usually talk about those things, we're talking about from the surface of the Earth. So when we talk about sea level, that local frame of reference would start from, well, the surface of the sea, and then that would extend out. When we're talking about space systems, that extends to the core of the Earth, right? Because that's where the center of attraction is, and that's all to do with the gravitational force and acceleration and all of those things. Those don't concern you at this point, but what I'm trying to get at to at this point is that frame of reference is modifiable. It changes with the system. So if I were to look at the entire galaxy or the Milky Way, I would be looking at it from the center of that Milky Way, right? So that would be my frame of reference. If I was looking at the solar system, I would be standing in the center of the sun, and I would be observing the motion of all the planets from the center of, or I would be trying to pinpoint the locations of all the planets from the center of the sun. So that would be my frame of reference. Sorry. And then in this case, what I'm trying to do is, since I'm observing ISS, I'm standing in the center of the Earth, and that's where my frame of reference is lying, and that's where I'm locating the position of ISS. Now, if you were to move on to essentially the same slide as I showed you before, right here. So we've got, again, UD, CJ. What I can do in this particular image is I can draw my frame of reference right here, which pops up as this red line. And let's say I'm standing right here at the origin. My one displacement to University of Dayton could be this part, and then this yellow line is representing the displacement to CJ from this point. And the displacement from University of Dayton to CJ is going to be this. So what we've learned here today is well, what we've learned here today are two things. The distance versus displacement dilemma, right? One is both are measurements of space between 2 points, but one is to do with the shortest measurement, so the straight line measurement, and that's displacement. The next one is distance, which does not take into account the shortest distance, shortest space, but it's essentially the measurement of space you undertake when moving from point A to point B, or in this case, moving from University to CJ, right? And then we were talking about frames of reference, which is essentially, and depending on the problem that you're trying to solve for, it can be changed, it can be adapted, and it provides you with a system here. Now, in this case, this is a 2D system again, with a way to measure that space, right, or those displacements or that distance. That's what it enables you to do, and it's a reference point, um, or centered, or the frame of reference is centered at that reference point, right? And there's that displacement slide which I'd forgotten about. So when I was talking about reference frames, let's start with our the Earth system, right? So when we're talking about the Earth system, it's not writing, sorry. So when we're talking about the Earth system, let's just assume this is the Earth, right? What we do is we go to the center, right? And we will point one axis up. So that's our Z axis, usually our Z axis. We've got our X axis, and then we've got another Y axis, right? And what usually happens is these are mutually orthogonal. What that means is that they are 90 degrees to each other, these axes. The angle between them is 90 degrees, right? So that's 90 degrees. And this little dot here is our origin, usually denoted by an italic O, right? So with this little case, when we're talking about our space systems, we can, let's say this is our little satellite here. Um, You can then point pinpoint its location at any given time. Let's say this is location P right here with reference to the center of the Earth. Now, this radius will change depending on where you're located on the surface of the Earth, but we know that, right? So we can measure that distance from the surface of the Earth. So uh, that's one thing. Or, see, I said distance. You can also do displacement. If you were going to give this a direction, which is usually upwards, but upwards based on the latitude or the longitude, that would be another thing, right? Where which sector does it fall in, that sort of thing. That would be then displacement. Moving on to, if I were to go on to, let's say, an example similarly, this again, this entire system is used for your not only satellites but also for your, this is the tilt of the Earth, but also for your aircraft, right? So if I were to draw a plane right here, that's one thing. It's a bad looking plane, but it's very tiny. But you can map out the position of that plane from the surface of the Earth, right? So again, this goes down to the radius. This is the surface, and you can pinpoint that location. Now this is going to be a separate frame of reference where your origin is starting from this, the surface point of the Earth, right? So again, Y, X, and Z. So that's one way to do it. When we're talking now, you can also do what I talked about in the 2D part. Was if I were to, let's say, if this is the United States right here. Um, this is Canada up top, and Mexico and South America. It kind of goes that way. But if I were to zoom into this little section, what would here happen is you'll get this little frame where you've got all these different states that are going through. Uh, right? So if I were to look at these, sorry, I don't know the map of the states or where the borders are, but essentially what you can do then is you can do a two-dimensional frame of reference right here, right? Let's forget Z because we're not dealing with Z or height anymore. We can do X and Y. So here's Y, here's X. And let's say if this is Dayton right here, um, my frame of reference, and if I'm sitting somewhere down here, let's say um, Arkansas, for example. For some reason, I'm there. Um, I can then measure my displacement. So that's my
location, right? So my shortest distance to Dayton. However, if I were to go to Dayton, I would probably have to follow this some sort of route, and this would be my distance. This is my displacement, right? Um, and then this little route that I took will be my distance. And that's the difference between those two things. And my frame of reference, which is here x and y, is allowing me to how to measure these two different things, right? Which depends where we are located and whatnot. I hope this helps. This explanation is more helpful than the presentation, but I wanted you to have the presentation just because you have something there that helps you, that breaks down everything, and this little animation of what I'm doing on screen helps you with that explanation.
And that's the end of lecture. It's going to be a short lecture today because what I really want to focus on are the end of lecture and class assignment, which I want you to solve and submit by 5 p.m. on Google Classroom. Um, Please do the assignment professionally. So use your Google Docs, your Google Sheets. There's going to be some plotting involved. There's going to be so no hand scribbled diagrams, professionally drawn diagrams. Uh, Google Docs does allow you to do that. Um, so you can do that, or if you can draw professionally in your Google Canvas, please do so. That's an application that should already have been installed on your Chromebooks, so you can do that. Um, the Google form that I'm going to be attaching today with this lecture will include the problem areas from the last unit. So please let me know about those, and I'll try to, if there are significant problems, I'll try to do another video lecture from unit one, either on Thursday or Friday. Um, Depends how many problems we have. Um, and then the second section would have, or the second question would be basically problems from today's lecture. Please feel free to email me with your questions, um, and I'll try to reply as soon as possible. And that's it. Thank you very much for your attention and have a good day. Bye bye.